Hello once again, class, and welcome to another mock lecture. Today we're starting off great. Today I just wanted to do another related rates example, one that's a little bit more involved. So let's just get right into it. So if we continue on with the numbering from the last video, this is example number 4. It says a grain silo has the shape of an inverted circular cone with a base radius of 5 meters and a height of 10 meters. If grain is being drained out of the bottom tip of the silo at a rate of 1.5 cubic meters per minute, find the rate at which the grain level is falling when the grain is 6 feet in depth. So there's kind of a lot to take in here. First thing I did is I drew a picture. We know the base radius, which is actually kind of the top radius since it's an inverted cone, is 5 meters, and we know this thing is 10 meters high. We also know there's grain in it that's being drained at a specific rate. So, and by the way, I think it's important to point out, and I think I might have done this in the slides, this is a volume that's changing. This is like a dV dt sort of situation. We're losing some amount of cubic meters every single minute. So let's write down the stuff that we know. Oh yeah, there you go, right there. dV dt is 1.5, really it's negative 1.5 cubic meters per minute because we're losing grain. But all right, we have a radius of the grain. We have a radius of the base of the whole thing as well, that's 5, but that's not really important insofar as the equation that we're going to come up with, kind of. I'll get into why I said that in a second. We have the height of the grain, that's h, that's this variable. Again, we have the height of the whole thing, which we're going to use here in just a second, but it's not pertinent to the equation that we're going to actually use to relate these variables with. And then we've got v, which is the volume of the grain. We're trying to find dh dt. Right, find the rate at which the grain level is falling. That's a height, right? How is the height changing per minute? And then we know dV dt is negative 1.5 cubic meters per minute. So when we go to set up the equation that relates all this stuff, I'm just going to use the volume of a cone, which is 1/3 pi r squared times h. It relates the things that we need. It relates the height, which is what we want to try to find, and it relates that to the volume, and that's good because we know what dV dt is. What we don't know, though, is radius, right? If we differentiate this thing with respect to t, we're going to get a dr dt, and we don't have any information about dr dt. And so what I need to try to do is rewrite r, the radius, in terms of our height somehow. And that's where the 5 and the 10 are going to come into play. If you take a cross-section of this cone, such that you're looking at the height of the cone and then also the kind of the side of the cone along with the radius, you're manufacturing yourself a right triangle. And there's 2 right triangles that are embedded in this picture. One of them is the right triangle cross section of the actual container itself, which we know the dimensions for, and the other one is the grain height. Right, so the grain is in here. This is how high the grain is. It's got a specific radius, but the radius changes as time changes as well. The thing is, though, we don't know how the radius is changing in terms of time, but we can rewrite it in terms of h by way of similar triangles. We know that this radius over 5 should be equal to this height over 10. That's just similar triangle stuff. So by doing a little bit of algebra, really just multiplying by 5 and reducing 5/10 to 1/2, you get that the radius is 1/2 of h, and that's what I'm going to plug in for r. It means that our function that we're going to differentiate in terms of time now only has an h and a v in it, which are the 2 base variables, the 2 base quantities that we want to relate so that we can differentiate this in terms of time and thus relate their rates in terms of time. Okay, that's new. That's something that we did not have to do in previous examples. At this point, though, everything's the same as what we've done before. I differentiated this thing with respect to time. I got dV dt is equal to pi over 4 times h squared times dh dt. That is just some chain rule stuff. The pi over 4, by the way, comes from the fact that when you bring down the 3, there's a power rule. 3/12 is 1/4, and you're multiplying it by pi. But then you have to multiply by dh dt, which is what we're solving for. That's what we're trying to figure out. At this point, I just plugged in the known information. We know dV dt is negative 1.5 cubic meters per minute. We know the height that we're looking at is 6 feet. And so then I just did some algebra to figure out that dH dt is negative 1.5 over 9 pi meters per second, which means that it's decreasing at positive 1.5 over 9 pi meters per second. Which I probably, kind of looking back at this, I probably should have converted that into an actual number. I have no idea what that is. Pi is like it's 3.14, so like negative 1.5 is like approximately half of that. So what is this? This has to be something like 1/18th of a meter per second? Oh man, I don't know. It's probably something like 1/20th of a meter per second. And actually, it's not even per second, it's per minute. This is in minutes, is what we're looking at, because our rate's in minutes. Okay. It's probably like 0.05 meters per minute that it's falling. That's what I'm going to guess. I'm going to check with a calculator after this and hope I'm right. Anyway, that's it. Really quick video. Just wanted to do one more example of this stuff. So hopefully that was helpful. If you have any questions or comments, leave them below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.